Hello there, my name is Ben and welcome to this math video tutorial on proof techniques. So we're going to learn, a few techniques of proof, how to prove some mathematical statements. And the first type that we're going to learn about is the direct proof. And the direct proof is usually a technique that you usually maybe want to go because it proves it directly, just with the statement, not really manipulating the statement that much. So let's say you have a mathematical statement in the form if P then Q. So P is the antecedent or the hypothesis, and then Q is the consequent. The way that you're going to prove this kind of statement is you're going to assume that P is true. You're going to assume P is true. And then you're going to use that assumption for P to prove that Q is true. So this is a direct route that you want to use to prove this kind of statement. You just use the assumption from P, and then you get and then you just keep implying until finally you get to the statement Q being true. So just working from one side of the logical bridge to the other side. It's another type of proof, which is called the indirect proof. And just like the word says, indirect means it's not a direct way of proving. And there's two important types that we want to look at. So let's write our original statement down. If we have if P then Q, one indirect technique of the proof that we can use is called proof by contrapositive. And the proof by contrapositive means that we're going to take the contrapositive of this conditional statement, if P then Q. And so if we remember what contrapositive means, that means that it's like taking the converse, but you're negating both statements P and Q. So it's going to be if not Q, and then not P. Okay, so that is the contrapositive, proof by contrapositive. So just taking, it's like the converse, switching the roles of Q and P and negating both of those statements. And then what we're going to do after that is take a look at another indirect proof, which is called contradiction. And the proof by contradiction, we basically have our same conditional statement, if P, then Q. And so what we're going to do in this technique is that we're going to assume P is true, and then we're also going to assume, as they say, on the contrary, that not Q is true, so we're going to negate the consequent and say that's true. And then from these two assumptions here, assuming P is true, assuming that not Q is true, we're going to arrive to a contradiction. So we're going to, that'll lead us to arriving to a contradiction, something that doesn't make sense, like P and not P. And we'll go to an example of how that works. We'll see a proof of that contradiction, and we'll actually see an example of how all these techniques work. There's also another type of proof technique, but it's more like disproving a statement, showing it by counterexample. So we'll take a look at that as well. So let's get started by looking at some examples with proof, starting with the direct proof technique. So we need a new board. So here's an example of direct proof. So we're going to say if M, is an odd and N is even, then we're going to say M plus N, sum of those two numbers, is odd. That's the statement we want to prove first. Okay, so we'll write out our proof here. And we're going to say let M be odd. So that means that M is, we could say, equal to 2k plus 1 for some integer k, and then we're going to let N is in Nancy, be even. And so N is going to be equal to, let's say, 2 P, and P is an integer. So this notation here on the side, K and Z and P and Z, these mean that K is in the set of integers and P is in the set of integers, and Z is a set of integers, that script looking Z. And now we're going to find out what M plus N is. M plus N is equal to, then we have M is 2k plus 1 plus 2p. And then that's going to be equal to 2k and plus 2p plus 1 equals, and then we're going to factor out a 2 here with the k and the p, so that's 2k plus p plus 1. And you can see that k plus p is also an integer as well, and 2 times that's going to be even. And since any even number added to 1, that will make it odd. So we can say, so M plus N is odd. And there we go. That's the end of the proof. And then we put a little symbol there to show that we're done with the proof. Okay, great. So all we did was we assumed that the antecedent m is odd and is even is true, and then we defined what in terms of the equations what odd and even integers look like, and then we add those two integers together, and then we use the fact that 2 times any integer is even, and if we add that to 1 we get an odd integer. Okay, so let's look at another example. We need a new board. So if we have next statement, which will let x and y be positive real numbers, and then we'll say if x squared is greater than y squared, then x plus y is less than 0, or x minus y is greater than 0. And we'll prove it. So we'll start out assuming that x squared is greater than y squared. And then here, after we assume that, we need to arrive to these two cases, x plus y is less than 0 or x minus y is greater than 0. So how are we going to arrive to that conclusion? So what we're going to have to do is do a little scratch work here on the side, and we will include this in the proof, but we're going to work with this inequality here and see if we can get something like this. So let's work that to the side. This won't be included in the proof. So we have x squared is greater than y squared, and we can see that if we subtract y squared to both sides, we get x squared minus y squared is greater than 0. And then if we factor x squared minus y squared, we're going to get x plus y, x minus y is greater than 0. And then we can do our little number line here. Solving for x, we need to see that we have a negative y and positive y. And so we can see that for x, you know, if here's our 3 different cases. So x is less than negative y, so you could plug in something like negative 2y, and you can see that that's going to be positive. So this is part of the solution. If we choose a number between negative y and y, say like 0, we're going to see that we're getting a negative number. So we can cross this possibility out. And then if x is greater than y, say 2y, we see that that's going to be positive as well. So there's our 2 cases. We have x is less than negative y, or x is greater than y. So then we can just put that back in. So we can say then we have x squared minus y squared, which is x plus y. X minus y is greater than 0. So this implies that either x is less than negative y, or x is greater than y. So if we add the y to both sides in the first inequality, we'll get x plus y is less than 0, or and subtracting y to both sides in second inequality, we get x minus y is greater than 0. And then there is the proof. We can put a smiley face there. See, and we're done. Yay. So this one we had to do a little scratch work here on the side, and that was with the inequality, because we had to subtract. We saw a difference of squares, we factored those, and then we laid out our number line, and we saw the two possible solutions to the inequality. They're greater than 0, and then we basically just brought the y's over to the other side, and then that reached our conclusion for the two different cases. Okay, so those were a couple examples of direct proof. Now we're going to take a look at some examples of indirect proof using the contrapositive and contradiction. I'll get a new board. Okay, so here's the contrapositive example. So let's say if p squared is odd, then p is odd. So if we look at this, we could try to prove it directly. It's just that we have the square there, p squared is odd, so that might be a little bit difficult to do. So this is where we need to start with maybe p to the first power first, bringing that as the antecedent, and p squared is odd as the consequent. So reversing those roles, but remember when we're doing contrapositive, it's like the converse, but we have to negate both statements. So we have to negate p squared is odd and p is odd. So when we do our proof, what we're going to do is say we will prove contrapositive. And then we'll put like this in colon here, and then tell what the contrapositive is. So that's going to be if p is the negation of odd is even. So we can say if p is even, then we can say that p squared is even, because that's the negation of p squared is odd. P squared is even. And there you go. That is the statement we want to prove. So we're going to let P be even. And so that is, let's say P is equal to 2m, where m is some integer. And then we're going to find P squared. So then, P squared equals 2m, all of that squared, equals 4m squared. And then this is also equal to 2 times 2m squared, right? Because 2 times 2 is 4, and with the m squared. So we see that 2 times the integer, 2m squared, that's also an integer. So we know that this is even. And then we're done. There's the proof. Okay, so that's a proof by contrapositive. Let's take a look at proof by contradiction. So we need a new board. So we're going to have let x and y be, let's say, positive real numbers. And then we're going to say x plus y is greater than or equal to the square root of 2xy. X plus y is greater than or equal to square root of 2xy. And that's the statement we want to prove. So here's the proof. So let's see. Let's rephrase this this statement right here. I'm going to rephrase this instead of saying let. Put this in an if-then form. Let's do if x and y are positive real numbers, and then we'll say then, here we go, x plus y is greater than or equal to the square root of 2xy. And now we'll do proof. So we're going to let x and y be positive real numbers, and then we're going to assume on the contrary that, and then we find the negation of this statement, x plus y is greater than or equal to square root of 2xy. So the negation of that would be x plus y is less than square root of 2xy. So the opposite of greater than or equal to is just strictly less than. And then we're going to use that inequality to get a contradiction. So how do we do that? So what we're going to do is we're going to square both sides of this equation. So we'll have then x plus y squared is less than square root of 2xy, all of that squared. And that's going to imply that we have x squared plus 2xy plus y squared is less than 2xy. And then that's going to imply that you see the 2xy's are going to cancel if you subtract both sides, and then you're going to have x squared plus y squared is less than 0. And we see here that x squared plus y squared is less than 0. Well, when we have the sum of squares, you know, just doing some scratch work here on the side, if they're both 0, and square that, then we know we're going to get 0, so that's false. It can't be less than 0. And then say if you have both positive numbers, like 3 squared plus 4 squared, well, that's 9 and 16 is 25. That can't be less than 0. And then if you have, say they're both negative, then you get 4 and 1 is 5, so that can't be less than 0. And then if one of them is positive and let's say the other is negative, or vice versa, you can see that that's going to be also positive as well. 36 and 49. 36 plus 49 is 85. So that's also going to be positive. So you can see this will never be negative. So we can say we have obtained a contradiction. And then we can say, so the original statement is true. And then we can put a stamp of QED on that one. There we go. So that's how you prove something with contradiction. You assume the hypothesis is true, and then you assume on the contrary the negation of the consequent, and then you use that assumption to come up with something that is false or contrary. Sometimes you may say something is equal to 1. You work out the equation. It's not equal to 1. So 1 does not equal 1. That's a contradiction. So you know, therefore, the original statement is true. And that is how a proof by contradiction works in a nutshell. Okay, so there's also one more thing I wanted to go over, and it is kind of like a proof technique, but it's more like kind of disproving the statement using counterexamples. So we can talk about that. And so we need a new board. Using a lot of new boards for this for this video, because there's a lot to cover here, obviously. But hopefully these examples will help you with learning the proof techniques. So we're going to look at counterexamples here. So counterexamples are basically examples that show why a statement is false. So let's look at a couple of mathematical statements, maybe using counterexamples. So you can say an example here is, like someone may claim all triangles are equilateral. So what does that mean? It means that triangles all have the same side. All their sides are equal length, and also the angles across from those sides are also congruent as well. Angular, equilateral as well. But of course we know that is false, right? And we could come up with an example to show why that's false. So the counterexample we could use is, there is a, you could say there is a triangle that is that is a right triangle. There's a triangle that is a right triangle or isosceles. And of course with right triangle, you always have a 90-degree angle here, right? And so you can see that all the sides are not necessarily the same. You may have a right triangle that's isosceles, where the two legs are congruent, and then of course your hypotenuse being longer than those two sides. It's different length. So, those are, that's a counterexample. You could find more than one. It could be isosceles, could be a right triangle, could be a scaling triangle, a triangle where all the sides are different, all the angles across from the sides are different. Oblique triangles. So the list goes on. So let's talk about prime numbers. Someone may claim that, every prime number is odd. But then once you go through your list of prime numbers, you do 2, 3, 5, 7, 11, etc. You can see that there's a prime number, the first one, 2, which is even. So you can see that 2 is a counterexample to the statement every prime number is odd. So we can see that statement's false because the first prime is even. And then maybe looking at one more example before we finish here, someone may claim that let's say for all integers, positive integers n, say n in the natural numbers, that n factorial is less than or equal to 2 to the n. So they may claim that this is true. So we can, test that statement out and see if we can find an example that shows that this inequality is false. So we start going through all of our natural numbers. 1, 2, 3, 4, 5, etc. So we start with 1, so we know 1 factorial less than or equal to 2 to the first power. That's true, because 1 is less than or equal to 2. 2 factorial less than or equal to 2 to the second power. Well, that's 2 is less than or equal to 4. That's also true. 3 factorial less than equal to 2 to the third power. So that's 6 is less than equal to 8. Well, that's also true. What about 4 factorial though? Less than equal to 2 to the fourth. So 4 factorial is 4 times 3 factorial. 4 times 6, 24. And is that less than or equal to 2 to the fourth? That's 16. That's false, right? So we just found a counterexample. So we see that there's an n such that when n equals 4, we see that n factorial is actually greater than 2 to the n. And then if you continue on with n equals 5 and then so forth, you'll find out that the n factorial will grow a lot faster than 2 to the n, and it will overtake it for n greater than or equal to 4. So that was the counterexample, n equals 4. Found that statement to be false. Okay, so that is all we're going to cover for this video on proof techniques. Stay tuned, for the next video. We're going to cover proof by induction. We'll talk about that. It's another proof technique, and we'll look forward to seeing you there. Again, my name is Ben, and thank you for watching this math video tutorial on proof techniques, and we will see you next time. Take care. Have a good day. Bye-bye.